Is this on? Can you hear me?
Don't. Can you talk?
Hello? Hello? There we go. Okay. So some previous speakers noted that they found themselves in the first picture the picture from the first Spirit of Leo conference. I also found myself in there. That was probably literally the third scientific conference I had ever attended. I probably absorbed 1% of what was being said in the room. And also making an appearance was my hair. So that was a long time ago. All right, so let's get into it. It's in the name, the Habitable Worlds Observatory. We seek to scientifically address this question for the first time in human history. Believe it or not, this is a question that humans have been asking for thousands of years. Before we even knew what stars or planets were, we've been asking this question. As shocking as that may seem, it's in the historical record. So if this is our goal, if we're trying to be this ambitious, we need to get this right. And how are we going to answer this? Well, there's a few key ingredients that I'll go over. The first one is why we're here today, which is high contrast imaging. We want to be able to take an image that looks something like this. Maybe we won't be making movies very often. This is a simulation from Corey Spohn. This is using the results of our end-to-end modeling, estimating what the speckle field will look like. Now, when we made these simulations, we didn't have all the control loops included. We didn't understand post-processing. So this is a real wag at what the image might look like. But we are building up the tools to be able to do this. And we will continue building on the performance of previous missions that have come before us. So HST, JWST, ground-based performance, Roman coronagraph. We are still going to have to improve things by at least an order or two, order of magnitude or two. We are also going to have to push on the working angle. So we're talking about working angles on the order of 50 milliarcseconds, 40 milliarcseconds, very small inner working angles. And it's fairly easy to make a plot like this and tell the chronograph designers this is what we need. But it turns out that, as most of you know, chronograph performance is multivariate. And we need everything. We need throughput, we need bandwidth, we need robustness to different aberrations. So we are asking a lot of chronograph designs to make this happen. The second key ingredient is the ability to search for biosignature gases and signs of habitability. If you were to look at the modern Earth's spectrum and spectra that we think represent the Earth through history, you're going to see a number of key features at different wavelengths. So, for example, molecular oxygen is in the visible. Water is also more or less in the visible. If you want to push out into the near infrared, that gets us access to methane, carbon dioxide, carbon monoxide, which is really important for false positive discrimination. And one thing that's really important for false negative discrimination is access to the near UV so that we can detect ozone. If your abundance of oxygen is not high enough, you may not see molecular oxygen, and yet its byproduct of ozone could be readily abundant. So we think we need most of that wavelength range. And the final key ingredient that we need is a useful sample size. If I were to give you this bowl of M&Ms and blindfold you and tell you to take one, the odds of you getting a blue one would be very small. But if I allowed you to take a whole handful, the odds of one of those, at least one of those being blue, would be pretty high. So luck is not a strategy. We have to create our own luck, and we need to be thinking about scientific productivity for this mission. We can describe this luck, if you want, with basic Poissonian statistics. And so this chart shows you that what your ExoEarth candidate yield needs to be to guarantee at least one planet that shows remotely detectable biosignatures as a function of the fraction of them that actually have remotely detectable biosignatures, which we don't know. So this plot allows you to understand the gamble that you are making with the universe. So in other words, if we wanted to design a mission to be robust to an F sub life of 10% with 95% confidence, we are going to need to be aiming for 30 rocky planets in the habitable zones of other stars. Now, this doesn't make the decision for you, but something that I think really helps clarify the decision is the math behind this chart is the same as the math that tells you what you learn in the event of a null result. Okay, so in other words, if we survey 30 rocky planets in the habitable zone, and none of them show signs of remotely detectable biosignatures, then we will be able to constrain that fraction to be less than 10% with 95% confidence. And this is very powerful. This means we have the opportunity to design a proper experiment to test this hypothesis and quantitatively address just how alone we are, regardless of whether the universe cooperates. This sort of hypothesis testing is how the project is thinking about this mission, and it's probably also part of the reason why the Astro 2020 Decadal recommended roughly 25 exoearth candidates for our goal. We have the tools available to predict the scientific productivity of this mission, to trace coronagraph performance and stability and things like that, down to the number of planets we expect to find. Rhonda Morgan is at this meeting. She's been doing a lot of yield calculations for us. A number of us, Dmitry Savronsky, Corey Spohn, I'm forgetting a number of people, are all doing these sorts of yield calculations. And we don't just predict a single number for the yield of exoearth candidates. We can actually average over all of the astrophysical uncertainties that we think feed into this. And so what I'm showing you here is just an example of what a yield distribution looks like. This is not the yield distribution for HWO. But you can see that we have a fairly narrow red line here. This includes all astrophysical uncertainties except uncertainty in eta Earth. And this very broad purple line includes the uncertainty in eta Earth. And so as you can see, the uncertainty in eta Earth is our dominant source of astrophysical uncertainty. If you know how to reduce that, I'm all ears. But right now we're using these sorts of histograms to understand what the possible confidence is in achieving a given yield. We are building on many studies that have come before us, all the way back to TPF, ATLAS, HGST, LUVOIR, and HABEX. Before START and TAG spun up a couple years ago, EGZEP funded a couple of critical studies. You can see Russ Belikov's poster on the chronograph design survey. When START and TAG spun up, we got all these fantastic science case development documents from the community. We have read all of those. We are trying to understand how those drive the mission, and we're working now with the CSIT to better understand the constraints that they place on the mission. There were a number of working groups that were spun up as well. Mike McElwain has a poster out there on the ConOps and post-processing working group. And the TAG spun up a number of very important parametric chronograph studies where we were looking at very high-level questions that we needed to answer before we could design this chronograph. So, for example, Brianne led a study understanding how polarization aberration affects our ability to do coronography and what actually matters and how you design so that we can do dual polarization coronography. And Pen Chen led a study on diachroic beam splitters. We would really like to be able to run in parallel multiple coronagraph channels, and that puts extreme constraints on the diachroic beam splitter. My understanding is that John Trauger has now submitted a paper on those constraints to be published. And as I mentioned, now we have the community science and instrument team co-led by Evgenia Shkolnik and David Charbonneau that are helping provide input to the project to design this. And most importantly, all of the many individual contributions by people like you in this audience. I'm really blown away by the posters that are out there, all of the technologies that are now being developed that are very applicable to this mission. The approach that we've taken for design and analysis is very much iterative. So when we started off with START and TAG, we created these things called exploratory analytic cases. These are sort of like notional mission designs, but they're not really designed, they weren't chosen around scientific performance. They were chosen to push on the boundaries of engineering and understand, you know, the trade space that we were working with. So we explored on and off-axis telescopes, different segmentation patterns, different aperture sizes. And over the course of about a year and a half, we put a lot of fidelity into those models. You can just see that from the illustrations here. Behind the scenes, we have teams working on, you know, thermal stability of these. We have, you know, people working on the solar arrays. And in fact, EAC-1, we are still studying. This is basically a baseline mission for us to go into extreme detail and study, for example, the stability of ConOps and the speckles that result from that. We are now moving on to two new EACs, EACs 4 and 5. Both of these are designed more around science, so they're pushing on aperture size a little bit more. EAC 4 is going to look a lot like EAC 2. It's an off-axis, non-deployable telescope, probably on the order of 6.5 meters or so. And EAC 5 is really pushing on aperture size. So this is also an off-axis hex pattern, but it's going to have an inscribed diameter somewhere on the order of 8 meters. We will then, after we go into detail on these for about 2 years, we will come up with EAC6, and we expect that EAC6 will be what takes us into MCR. But even EAC6 will not be the final design of HWO, so we still have years of iterating this design ahead of us. HWO will achieve robust exoplanet science yields. We have been charged by headquarters to have robust science margins, and we've been doing a lot of thinking about that. And one of the main trades that we know is ahead of us is a trade between aperture size and how many technologies you want to mature. So here's an example. We took EAC1, which again was not designed with scientific performance in mind, and we came up with a whole list of maybe a dozen design changes. We gave it to the engineers. They ranked it by perceived pain, if you will. And we then said, well, if we had a 6 meter or an 8 meter, here are the exo-Earth yields you can expect for those. And so just as an example, let's say our goal on this chart was 49. If that's your goal with a 6 meter, you're going to have to invest in all of these design changes and technologies to hit your goal. If you launch an 8 meter, you don't have to advance in very many of the difficult ones, and none of the ones that are truly, we think, extraordinarily challenging. So I'm actually going to conclude the overview portion of my talk here and move on to a second portion of my talk. But I want to echo some of the comments that, or the spirit of Marshall's talk. It was a really great talk when he opened it up on reviewing JWST. And Marshall went through all of the amazing technical performance of the instruments and the miracles that JWST had to solve to get this to launch. But at the end of his talk, I think he said something really profound, which is looking back on it, what actually got JWST to launch and what is getting the science. And I think he can summarize that by teamwork and hard work. And HabWorlds is going to be just as challenging, if not more challenging, than JWST. This is bigger than any one of us. It's bigger than the project office. And quite frankly, it's bigger than any one space agency. We need partners on this. We need international partners, and we need your ideas and your creativity, and we need to get to work. So in the spirit of sort of getting down to brass tacks, I would be remiss if I didn't really focus most of my talk on the single hardest thing we have to do, given the audience in this room. And that is achieving our noise floor. What I'm showing you on the right is from the technology maturation roadmap. We went through and categorized all of the technologies we have to advance by importance and lead time. So is it simply an enhancing technology, or is it something we need to have a mission at all? Is this something we need to start in the next few years, or is it something we need to effectively have started yesterday? And I'm going to highlight these 4 critical things in the top right corner and a couple of the ones in yellow down here. Here they are on the left. They all relate to stability, contrast stability, post-processing, and the noise floor ultimately. This is the single hardest thing for HabWorlds to do, and we could use your help figuring out how to do this. The reason that this is so hard, you're probably familiar with hearing that HabWorlds is going to achieve contrast of 10 to the negative 10, but the honest truth is we want to see planets slightly fainter than that, and we need to detect them at an SNR of 7 to 10. That means our 1 sigma noise floor has to be 3 times 10 to the negative 12. This is not news, actually. A number of people have known this for years. We've had publications on it. Bijan Namadi published back in 2024, actually about 5 years ago, he was talking about this. Stuart Shacklin has published papers on this. And actually the yield calculations have been around for a decade, have basically shown this. And we did an internal study this past year to confirm it. So this is where we need to go. This is very difficult because if you try to get to a 3 times 10 to the negative 12 noise floor with differential imaging, it's going to require potentially extraordinary stability. So Bijan also showed this in 2020, where for differential imaging, your tolerances are on the order of a single picometer. Now, our team is looking at that internally. So we have set up an end-to-end system modeling effort. I encourage you to stop by Charlie Necker's poster to learn more about this. But we are taking effectively what is Roman's OS 11. It's operating, it's ConOps. We're calling that our OS 1. And we're simulating, if you do RDI and ADI, here's the roll and pitch angle of the telescope over time. And we're predicting what this speckle pattern looks like in very high fidelity. Now, we don't necessarily think we're going to do RDI and ADI. I actually think neither of those might work for this mission. But this gives us a really good starting point to understand what the driving challenges are with stability and how to do post-processing, get down to that noise floor. And largely speaking, I don't want to ruin Charlie's poster for you, but we're achieving similar to numbers to what Bijan showed. So this is going to be very difficult. All right, so what can we do about this noise floor problem? The first thing we can do is obviously some smart engineering. We can control the modes that matter. So this is a block diagram from our HWO tech development plan. You can see in here we have things like edge sensors. We're considering capacitive and optical edge sensors on the mirrors, a laser metrology system to understand the location of the secondary relative to the primary. We have a LOFUS control system talking to the fast steering mirror, a HOFUS control system talking to the DM. We're even looking at additional control loops like a DM drift sensor. So we can always add another control loop to try to control the problem, but obviously that adds complexity and is challenging. So another plan that some of us are starting to look at is, I wonder if we can do post-processing that doesn't require picometer stability. And this is a project that I've been working on with Susan Redman and Russ Belikoff that are here, as well as a number of other people on this slide. All right, so JB had this wonderful talk on post-processing, overview talk on post-processing, where he reminded us that post-processing is not just one step. It's not just PSF subtraction. It's a whole series of steps, and we have to think about how they're all connected. And so if I were to list out the main steps of how you go about detecting an exoplanet in direct imaging, the first step is obviously how you design the mission, right? You need to design a mission that can conduct the observations in the way you want to conduct them. The second step is your CONOPS, how you go about collecting data. And you have to choose a CONOPS that allows you to perform the PSF subtraction algorithm that you want to use. So all three of these are connected. We've heard a lot about these at this conference. But there's actually a fourth step we have not heard too much about. JB touched on it a little bit, and that is signal detection. There is something we do to the data to tell us, have I seen a planet or not? And typically, we'll start over here on step 1, and we'll say, oh, well, let's design a notional mission, EAC1, and we'll sort of come down here, and then somebody will say, well, what if we added a third roll angle instead of 2 roll angles? And then you'll come back and you'll say, oh, well, can we do a third roll angle? And they'll say, well, I had a planar sunshade. If you had a third roll angle, the thermal state is totally different. So you have to redo your mission design. And it's a very clunky process to go from left to right on here. And so what we thought about doing, what I'm going to present here, is starting over here on the far right, talking about the extreme basics of signal detection, and see if there's any lessons we can learn that we can then flow to the left. So the rest of this talk you can think about basically as the opposite of the machine learning talks. We're going to go to fundamentals and start off with the basics of signal detection. And to do that, I first have to talk about what we mean by we detect a planet at 5 sigma. You've seen a lot of people saying that in this conference. It's in publications all the time. Typically, what they mean is that they have an SNR of 5, right? And so they went to their data, they measured their signal, they estimated what the noise was, and that ratio was 5. But what they're implying, what we are implying, I'm guilty of this too, is that we have a 5 sigma confidence, okay? And that's not necessarily the case. SNR is not necessarily a good proxy for confidence. So SNR can mislead us if the noise is not Gaussian, okay? That's the regime we're working in. We have a small sample of data. Dimitri showed this in his 2014 paper. We use nonlinear processing techniques. I guarantee you every single one of the pipelines we've talked about uses nonlinear techniques at some level. Or we measure SNR incorrectly. So we are all doing this all the time, and I think we need to be really upfront about the confidence that we're talking about with our detections. I'm going to hammer home on this last point a little bit. By the way, I'm just going to throw out some ideas here. I think this is the perfect audience to critique some of these ideas. So in the spirit of trying to make progress, I'm going to throw some ideas at you, and you can tell me why I'm right or wrong. All right, so I think we are largely measuring SNR incorrectly, at least when it comes to detection. Detection and characterization are statistically 2 different questions. With detection, we're asking, what is the likelihood that this blob isn't noise? And with characterization, we're saying, I've decided the blob is signal. How precise is my estimate of its flux? You'll notice that neither of those questions have anything to do with SNR. right? The one on the left cares about what is your false positive rate. The one on the right cares about what is the precision of your flux estimate. SNR is simply a proxy that we use to try to communicate those other two more important things. Now, the problem is, if you ignore the signal in your measurement of detection SNR, it's like deciding you have a signal already, and you will inflate your SNRs. So that might sound philosophical, but I can prove it to you. You can take the easiest toy model you can imagine and just generate random Gaussian noise, process it with a pipeline. I'm showing you 3 different pipelines here with different colors, the details of which don't matter yet, and apply your detection method to that data that just has noise in it. And if you ignore the brightest point in that data, you will bias your SNR. You'll end up with these dashed lines where the apparent SNR no longer crosses the expected confidence at the right point. If you include the brightest point in your pipeline, now you can now your SNR is more or less related to your confidence. Unfortunately, this has the side effect that there exists a theoretical limit on what your detection SNR can be. It's given by the peak of your signal divided by the standard deviation of your signal, and it's measured over a certain number of samples in your image. So I'm showing you that limit here. This is the limit on detection SNR as a function of number of resolution elements used to estimate the SNR. And you can see at about 2 lambda over d, I've converted a number of resolution elements to a working angle up top, assuming a 1 lambda over d wide annulus or a 2 lambda over d wide annulus. And you can see at 2 lambda over d, if we have a 1 lambda over d wide annulus that we're using, our theoretical limit is 5 already. So we're already encroaching on sort of the regime we want to be working in for Hab worlds. And it gets worse because, as many of us know, Dimitri had this paper showing that when you have a small sample size, the SNR is now, sort of decorrelated or decoupled from the confidence. So not only is there a limit on our SNR, but it's not actually telling us about the confidence, and things are much worse than the SNR predicts. We need to figure out what this means. We need to figure out how to improve this limit. One way to do that is to ensure that more of our image, we can use a larger region of the image to estimate SNR. And that means that our speckle statistics need to remain constant over a larger portion of the image. How do we do this? I don't know. But it's very important that we calibrate our detection SNR and our characterization SNR. This is also a major challenge. If you're trying to calibrate your detection SNR to false positive rate, if you want to do it to 7 sigma, that means you need roughly 10 trillion speckle simulations with different Poisson draws, and that is going to be very challenging. Calibrating your characterization SNR is much more straightforward. You just need a forward model on the order of 100 planets or so. Okay, so with that warning in mind, I'm going to go into detail now on that last box about how we go about detecting a signal. And so let's start with the basics. Let's talk about aperture photometry. When an astronomer determines whether they have a planet in an image or not, what they do is they take the image, they'll put a circular aperture down on the image where they think the planet is, they add up all the photons in that circular aperture, and that's their signal. And then they'll repeat that process all across the image, take the standard deviation of that, and that's their estimate of the noise, right? In 1D, what that ends up looking like, I've drawn a array pattern on the left embedded in Gaussian white noise, and that's like taking a convolution of that 1D data set with a top hat function. So if you do that, you'll get the data on the right, and then you can compare the peak to the standard deviation and estimate your SNR. A convolution, though, is of course entirely equivalent to a multiplication in Fourier space. So instead of rastering that top hat across the image, we can take the Fourier transform of the data, multiply by the Fourier transform of the top hat function, and then when you take the inverse Fourier transform, you get the exact same thing as if you had rastered the top hat. Okay? Now, the key point here is that multiplying the Fourier transform of your data by anything is a spatial filter, by definition. So exoplanet detection is spatial filtering, and there may be lessons in spatial filtering that we can learn about to improve our detection methods. All right, so there are better filters out there. We've heard about match filters at this conference, right? I can't tell you how many times I've heard somebody say, have you tried using a match filter? All right, so what is a match filter? A match filter is basically a correlation of your data with the template signal you expect to find. And a correlation is just a slightly different convolution. So this is just like the case of the top hat. Instead of using a top hat, we're using the area pattern that we expect to find. So up here on the left, I have our data. Again, in the middle, what I'm showing you is something that's very important. This is the power spectral distribution, the PSD, the spatial PSD of our signal, shown in black, and our noise, shown in red. So basically what it is, I took the signal, take the Fourier transform, take its amplitude and square it. Do the same with the noise, and this tells you about the power distribution in Fourier space. And you can see that the noise here, bumps up and down a lot, but it's more or less constant. So this, if it's constant in Fourier space, that means it's white noise. Okay? In fact, that's the only way you can know if your noise is white. I think our field is guilty of calling all sorts of things white noise, but this is the only way to know that it's white. And it turns out that a match filter is the ideal linear filter that optimizes SNR in the presence of white noise. So if we run that match filter on the data set on the left, you get the output on the right, a very, very high SNR. The problem is that the match filter is only the ideal linear filter for white noise, right? We know we are working with correlated noise residuals. Detector noise is not always white. Photon noise is not white. And to show you, if we instead put correlated noise in with our little toy model of a signal and look at the PSD, you can see that the noise now has two sharp spikes at the positive and negative frequency of that sinusoid. And if we attempt to use a match filter, it fails horribly. Match filters cannot deal with correlated noise, and our SNR is greatly reduced. And so the question is, well, is there a better alternative out there if we know that we're dealing with things that are not, with noise that is not white? And the answer is yes. It's called a Wiener filter. A Wiener filter is expressed in the top right, and it is the ratio of the true signal's PSD to the sum of the true signal's PSD and the noise's PSD. And so here I'm showing you those same two data products, and we'll pass the data on the top left through a Wiener filter, and you'll see that they perform basically the same. In fact, the Wiener filter can outperform the match filter for a finite data set. And on the bottom, with correlated noise, you can see that the Wiener filter can suppress that correlated noise. Basically, the Wiener filter is a custom filter that removes noise and lets the signal pass through. All right, there's a problem with the Wiener filter, though. Formally, it requires knowing the signal and noise separately, and that's the whole problem we're trying to solve. So how do we deal with this? There's a lot of different recommendations out there. One of them is that if you take the Fourier transform, if you take the PSD, you can fit low frequencies to your signal and high frequencies to your noise and extrapolate them. That might work for something like JWST, where you have an incredible number of photons, or situations where your planet is much brighter than the speckles. Probably is not going to work for Habworlds. So instead, something we can do is simply make the approximation that the denominator is the PSD of the data itself. And there's all sorts of problems that result when you do that, and so it's not super straightforward, but we can fix those. One thing to notice that if we do that, we now have a nonlinear filter. And there's nothing saying that the Wiener filter is the ideal nonlinear filter. So I'm also going to examine other scenarios where we simply have this form for our filter, and we vary alpha and we vary beta, and I'm going to call this singularly the optimized filter and see where we get with it. Okay. Now, before I move on and show you these filters at work, I want to state, I think, the most important take-home point of this talk, which is that the Wiener filter tells us what we should be focused on. It is the overlap of the PSD of your signal and the PSD of your residual noise after you've done everything to it in the integration long image. That is what we should be minimizing. It doesn't matter if you do ADI, RDI. It doesn't matter if you're designing an APLC or a vortex. This is the thing that tells us our ability to remove noise, remove speckles from the image. And so I think we should be focusing more on this. So there are many ways you could imagine doing this. You could imagine shifting this noise to other frequencies somehow. Maybe you dump these two outlying frequencies into the center frequency. You could sharpen and rarefy the noise PSD, or you could adopt a good basis set. I don't have time to get into that. And we should consider this at all stages of design. Okay, so now I'm going to show you a demonstration of applying these sorts of techniques to actual lab data. I'm inventing some terminology here. I'm going to call speckle shaping I'm going to refer to as anything that intentionally changes the noise pattern's PSD so that it overlaps with the signal S. And I'm going to then talk about a subset of that, speckle smoothing, where we attempt to dump as much of the speckle PSD's power into the DC component as possible. Okay? So we're sort of rarefying that noise power spectrum. There are a lot of methods out there that you could imagine using to do this. I'm only going to show you one method. That's a continuous roll of the telescope. Now, the ground-based community has been doing this for a long time, right? And so the effects of the continuous roll is already showing up in modern ADI algorithms, whether we realize that what we're doing is altering the PSD or not. But there are other methods out there. I'll touch on those at the very end. Okay, so we worked with Susan Redman. You can go visit her poster to use a data set from DST. This data set had a mean contrast of 2.7 times 10 to the negative 10 over 2% bandwidth. I'm showing you a single frame of that data set on the bottom left. You can see all this horrendous detector noise in here. It was a half dark zone data set. All of these ridiculously bright speckles are actually Susan's DM probes that she has injected. This is a dark zone maintenance experiment to maintain 3 times 10 to the negative 10 contrast. So the main problem in this data set for finding planets is actually not the raw contrast. It's the probes we're using to maintain the raw contrast. And we're going to admittedly cheat a little bit, and we are going to modify this data set by copying this upper circular portion here, rotating it 180 degrees and pasting it down here because we want to look at that continuous roll scenario. And the image on the right shows you what it looks like after you've maybe smoothed it a little bit if you're interested in that. This is a plot showing what the open loop drift would have been in this data. It is not picometer stable. She was injecting a random drift at 10 to the negative 10 per hour, and she was maintaining the 2.7 times 10 to the negative 10. Okay, so we took these data, we injected planets with admittedly a very precisely known Airy pattern. We assumed it was a translation invariant Airy pattern. And we scaled the number of photons to be relevant to Hab worlds. And then we did Poisson draw on that. And we looked at different roll ranges. We looked at different SNRs. And I'm going to show you now let me back up a minute here. Susan had 600 frames total in this experiment. The first 100 were all unique DM commands, and then she repeated those unique DM commands 6 times. So I'm going to show you one of those 600 frames after we've injected a planet into it. Would you like to see what the Hab world's image will look like? There it is. I sent this data to Kellen Lawson because he was starting to look at ADI on this, and he said there's something wrong with the data because when you take the median, it's all zeros. So we can't use medians anymore. This is if you scale the image such that you expect a photon noise of 7 in the final image. Now, if we increase the photon noise to 30 and stack all 600 frames, this is what you get. This is what it looks like with no roll at all. Obviously, the planet is very difficult to see. And if we do a continuous roll, this is if you want to smooth it by a 2x2 boxcar to get rid of that high frequency noise, it's still very difficult to see the planet. It's 2.5 times fainter than the raw contrast, by the way. If you roll it by 120 degrees, the planet becomes obvious. So these two data sets here are the same exposure time. One is continuously rolling the telescope, the other isn't. And your eye is picking out the fact that we've altered the PSD of the speckles by doing that. Okay, so I'm going to show you 15 pipelines that we considered. This is composed of 3 different types of PSF subtraction. I'm not going to do anything smart, okay? So I'm not doing RDI, I'm not doing ADI. Those probably would result in better results. I'm going to intentionally do really dumb PSF subtraction. So the first thing I'm going to do is no PSF subtraction. And then the second thing I'm going to do is this thing called arc fitting, where we, the speckles are have been rotated into arcs, so we go through and we fit arcs to the data. And the third option is where we do that arc fitting, and then we can see DZM probe residuals in the image, so you can kind of it ends up being periodic in nature, so we have a method to try to estimate and remove those. And then I'm going to apply, after you do one of those 3 things, 5 different types of spatial filters. So we're going to do the match filter, the Wiener filter, and the optimal filter in Cartesian coordinates, and then the Wiener filter and optimal filter in polar coordinates. To give you an idea of what this pipeline looks like, we take the simulated image for different SNRs and different roll ranges. If we want to work in polar coordinates, we do this transformation, we do the arc fitting and subtraction, we do the Desium probe residual removal, and then finally we either do a spatial filter in polar or Cartesian coordinates. And I want to emphasize here that we are only working on this image. We're not looking at individual rolls. Okay? We're not doing ADI where you work in the instrument frame. We're using one image with no knowledge effectively about anything that happened during the observation. So here are the detection SNRs when we have 2 flavors of PSF subtraction. And this is for each of the 5 filters. This is admittedly for a very optimistic case where the photon noise was set to an SNR of 30 and a total roll range of 120 degrees. That might be very difficult to actually build a mission that can do that. You'll note that we are not achieving our photon noise of 30, and that's for multiple reasons. Well, first of all, I mentioned earlier that there's a theoretical limit on your detection SNR. And so based upon how we're measuring it here, that turns out to be 17. Second, there's all that horrible detector noise in the data, and I haven't included how that affects our limit in this plot. The filters obviously suppress some of the signal, and so we lose our signal. And the filters leave some correlated noise. So at some level, they just fail, right? And you're stuck not achieving your limit. The encouraging thing here is that we are achieving a detection SNR greater than 7 on a planet that's 2.5 times fainter than the raw contrast in a data set that's 3 times 10 to the negative 10 and in the photon noise regime of Habitable. So that's all very exciting. Here is the detection SNR as a function of roll range. You can see the detection SNR goes up for all 5 filters. This is telling us that this speckle smoothing, if you will, is working. We're changing the PSD. And the very sobering thing is what the false positive rate looks like. Okay, so on the right is the false positive rate where it found something else in the image that was not the planet and has reported that it has found a speckle. It thinks it found a planet, right? And you can see that although this goes down and it is suggesting that our technique is working, it is nowhere near an 8 sigma result, right? We have an 8 sigma result. We have a false positive rate of like 20%. So this is why I was saying that calibrating our false positive rate to the SNR is critical. Okay, the more interesting case is what happens when we don't include any PSF subtraction. So these are the SNRs without PSF subtraction, and you can basically ignore the match filter here. It's completely nonsensical. But you can see that they do almost as well as a scenario in which we do PSF subtraction. So here the filter is handling all of the correlated noise for us. And again, we're achieving an SNR of 7 still on a planet that's 2.5 times fainter than the raw contrast. On the left is the SNR as a function of roll range. You can see that it does go up as a function of roll range. Again, you can ignore the solid line, which is the match filter. And what is most encouraging is on the right, I'm showing you the false positive rate. So you can see that the false positive rates drop much faster than in the scenario in which we attempt to do PSF subtraction. This could just mean that our sort of naive PSF subtraction is introducing correlated noise, right? But not doing anything turns out to work better. And shockingly, the Cartesian Wiener filter is 2 orders of magnitude lower in its false positive rate than all the other curves. And so it is basically pulling out planets that otherwise look invisible in these images. I'm showing you here what the input image looked like and what the filtered image looked like. The white crosshairs are where the planet actually is, and the red dot is basically where the filter finds the planet. So we have a lot of work to do on this. We need to rerun some experiments that have reduced detector noise. We need to investigate probe commands that don't inject horrendous speckles, right? That inject speckles with the right PSD that don't limit us. And we're also looking at other methods. So Scott Will has started looking into using EFC to minimize the overlap of the speckle PSD and the planet's PSD. And I think we can also do this fundamentally in coronagraph design and maybe even segment geometry. And lastly, really what we need to be focusing on is understanding whether this actually relaxes stability requirements or not. It's not entirely clear at this point. And so with that, I'll put this up there and take any questions.
Hi, Beck Dacus from UC San Diego. This is a fantastic talk, especially all of the continuous role stuff. That's something I hadn't thought of before. I wanted to ask about you said that the requirements for characterizing the detection noise and signal to noise sort of outstrips that for characterization by a factor of a few billion. So I wanted to ask what is primarily driving that and how that influences our sort of approach to detection and versus characterization observations.
Right, so you're talking about calibrating the SNR to the thing that actually matters? Yeah, so for detection, we're asking the question, what are the chances of being confused by a speckle? That means you have to sort of average over all possible speckle patterns that you could see. We only get one speckle pattern in a single image, but we have to know statistically what could have happened to confuse us with a planet. So maybe we don't need 10 trillion speckle patterns to go down to 7 sigma. Maybe we need 10 billion to go to 5 sigma. I don't know what the exact number is. But for characterization, it's a much different game because we're not looking for that amazing SNR. We're not looking for incredible confidence. We're looking for like a 10% flux precision. And that you can get with 100 forward models or so. Charlie.
Oh, okay, thank you. Thanks for this topic. It was great when you first presented it to our team. It still has things in it that I haven't fully understood. But one of the things that we still have to do is there are other ways of distinguishing planets from speckles, and we have to work through how the observatory behaves while it's doing those things, how it actually runs through the analysis. One of the things that I was thinking about with the continuous roll is you're assuming that the speckles are not dramatically changing during the roll, but we know that they will just because we have thermal models of the observatory that show that. So.
Yeah, so let me address that first. Yes, we ignored, we're using lab data, so we can't unfortunately inject what we think the wavefront error disturbance is going to be. So the results I'm showing are representative of a continuous roll under the assumption that your continuous roll injects less wavefront drift than what Susan was injecting. So the extent to which that mirrors reality, I think, has yet to be determined. But yes, I think there are a number of other things we can lean on here. You mentioned that we ignored some other aspects of differentiating speckles from planets. And so, this SNR limit that I talked about is only true if you have one image and that's all you have, right? But in reality, we're going to have multiple epochs of imaging. We're going to be able to fit orbits to these blobs and say, what are the odds that this is a reasonable orbit, right? That's what orbital differential imaging is. I think inevitably that's going to be part of the game. So there are a lot of other techniques out there. I'm very interested in where this goes in the spectral domain as well, once you're looking at a data cube. So yeah, this is just the start, hopefully.
Thank you. Thanks, Chris. That's awesome. So yeah, I had kind of the same intuition, but I didn't ask myself the good questions like you do. When I discovered a little bit the Roman chronograph data simulations back in 2017 from John Christ, where when you're really in photon counting mode, and you don't have much leak out of the chronograph, then I had the same intuition that basically PSF subtraction would not do much, which is not the case for most of our chronographic regimes on the ground and with JWST and stuff, where we still have a lot of leak from imperfect centering or simply photon noise, more photon noise from the speckles themselves and the star glare, right? So that's why we gain so much with PSF subtraction, and that's why I think in the case of hub worlds like that with a dark hole, that those are the right questions to ask ourselves.
Yeah, and actually you bring up a really good point that the degree to which this helps you depends completely on the regime you're working in. So, I've seen a lot of images presented at this meeting of planets embedded within residual speckles. And sometimes it's very obvious that there's still correlated noise in there. These sorts of filtering techniques would be fantastic for those images, right? Maybe you're not relying on the filter to do everything, but if you still have correlated residuals in your final image, you can touch it up with these filtering techniques.
I think we're out of time, but I encourage you to come and talk to Chris during the coffee break. You've given us lots of food for thought, so thank you. So let's give our speaker an applause.